Okay, good morning, everyone. So, 2 weeks ago, we start our lecture, so we're still in the introduction. So, in the 2 weeks ago, we mainly introduced the basic related semiconductor physics device and why we still need to put some efforts to understand and then try to push the boundary of our semiconductor technology for our for the demanding of our new application. So it's always to look forward, before look forward to the new technology, it's always good to review the evolution of our semiconductor technology from the very long time ago. So last time we had already mentioned the evolution of microelectronics from the early time. We have this vacuum tube. And then afterwards, the first transistor that we have developed is a bipolar transistor. And last time I already mentioned that the reason called the bipolar is because of this is a transistor involves two kinds of different carriers that operate at the same time, which is electrons and holes. So that's why we call it bipolar. The reason we have a bi here is because that's involved two different kind of carriers here. And then after the bipolar transistor, we start to have the MOSFET. So this is a simple schematic of the MOSFET. So as we already mentioned last time, the MOSFET is a structure that combined with, we have a metal here, we have a dielectric here, we have a semiconductor here. So that's why we have the name of MOS. And the reason why we call the field effective transistor because we need to apply the bias in somewhere. In the MOSFET, in most of the case of MOSFET, we only apply the bias in the gate side and drain side, and then we will ground it in the source. So the typical operation for MOSFET is once we apply the gate bias with enough gate bias, for sure we will start to attract electrons under the channel. This is because we apply the particle gate bias. So with this doesn't really need a very complicated physics. It's just a pretty simple high school physics. Once you apply the positive gate bias on one side, for sure you will start to attract electrons, right? So negative electron will try to flow to the positive gate bias. And because we have the dielectric here, so you can imagine dielectric just a kind of like the barrier, so that will stop our electron flow toward up. So that's why all the electron will stay in this region. And at the meantime, we will apply the drain bias on the drain side. So since the electron cannot flow to the top, but we have the positive drain on the drain side, so the electron will start to flow from source to the drain. In the end, become the drain current here. In here, I use the flow as an electron current. And then if you, in terms of the general current is flow into the drain side, but it would be more straightforward to use the electron to consider the most of the semiconductor physics here. So electron current will flow from here. So that's why if you look at the drain current versus the gate voltage here, as I say, first of all, we need to apply enough high gate bias. So once we apply up to a certain value here, we start to have enough electrons at this region. And furthermore, since we have the electron form under this region, this is usually we call as a channel region, and therefore we start to see the drain current increase because we still keep increasing our gate bias. At the meantime, we have the fixed drain bias, so the negative electron will flow toward the drain and become the current here. So if you can more or less follow what I say in the last 5 minutes, I would say you almost get more than like 70% to understand the most important operation for the MOSFET. Actually, it's not that difficult. Of course, there are some more difficult things because we face a lot of the side effect. We have many parasitic effect. We have lots of the non-ideal effect that make our MOSFET design is not straightforward as we expect. But the general idea is relatively simple. And as you know, it's only one carriers involved in the channel as shown here. So that's why that we will consider this is a very general, as we call the unipolar transistor, because we only involve for the one type of a carriers here. We only involve one type of carrier that can involve for the device operation here. So in here we only have the electrons operates in the channel, and that's in the case of the very basic MOSFET. So after we start to develop the MOSFET, for sure that we will not satisfy the typical characteristic of MOSFET. So we will definitely try to improve our performance of a MOSFET. In general, if we want to improve the performance of one transistor, the first things we want to focus is definitely the on current. So the on current is generally referred to the current at a high gate bias. So that's what we call the on current. And we actually, from the sum of equation that we will introduce, so generally we can expect our drain current is certainly proportional to our mobility. So if you have followed the electronics, then you should know that we have the drain current equation. That's a certain correlation with the mobility, but it also is quite straightforward, because the mobility inside these channels definitely will influence our on current or drain current as well. So the first effort is trying to improve the on current as shown here, and then there are several different strategies. The first one is we consider as a strain silicon. So we have the source and drain that we use a strain silicon to improve our channel mobility, or we can use a germanium channel, which will replace the silicon here as a germanium, or we can use a 3-5 materials. So these are the general approach that how we can improve the on current. Of course, there are more than methodology than we illustrate here. I think there are probably more than 1,000 ways to enhance the mobility. But in here, we just quickly go through the most well-known and then has been already realized in the commercial product, or has been proved that it is not possible to be realized in the commercial products. And that's the first step that we try to improve our on current. But the problem is that if we try to scaling our MOSFET, so the first step for scaling is we try to reduce every dimension as possible as we can. So we will reduce the channel length here. We will reduce this source region. We will reduce this drain region. We also will try to reduce the gate dielectric. So that's a general purpose related to what we call the scaling. And if we consider the scaling of a channel length, so ideally is we try to reduce the distance between the source and drain. But now we might face the issue is that we all know this is N plus in the source. We all know this is N plus in the drain side. So they could have the chance that the electrons in the N plus might be able to tunneling through the drain region, even when our gate bias is smaller than threshold voltage. So as we already explained in the last slide, that we only expect there's an electron in the channel once our gate bias is larger than threshold voltage. Therefore, we expect if our gate bias is smaller than the threshold voltage, so that means this region we don't have any electron. So ideally, we should not have any current. But the problem is that once our channel length is reduced, we figure out that the electron can be tunneled from source to the drain side, even there's no channel here. And this creates the issue of off-state leakage current. So therefore, you can see in the many of the reported literature or data, once our channel length reduced, we will see the off current is increased here. So the off current here is a log. We plot in the log drain current versus gate voltage here. So once our channel length reduced, our off current is increased. So this is mainly due to the tunneling. To further understand tunneling, we need to have the quantum mechanics. That's why I think in the next 2 chapters, we will start to introduce the quantum mechanics. So the concept of quantum mechanics, the difficulty of quantum mechanics depends on the purpose of why you have to study that series. If you are from the physics department, for sure that you can try to learn the quantum mechanics as a 1 semester, 2 semester with a very thick book. So usually in the end, everyone is completely confused what's the purpose of quantum mechanics. But luckily for our semiconductor engineer, to be honest, that we don't really need that very complicated quantum mechanics to help us. What we really need is how we can explain the carrier, the electron or holes, can transport from one region to the other region, even there's no bias, even there's a barrier. The barrier, it means that there's some kind of like the wall behind. So that's why we need to use quantum mechanics to understand. So that's the purpose. So basically we use like 2 hours with 1 chapter is enough for us to apply the quantum mechanics to analyze the case in the semiconductor world. So we will talk about this later. So now the issue is become, of course, we can increase on current as we try to do some channel innovation, do some innovation in the source drain. But the question is, once we reduce the channel length and our off currents increase, so therefore the figure of merit, the performance index that we pay attention to now is not only for the on current, but it's actually become the on-off ratio that we usually very often see in the many reported literature. They always claim that they want to have on-off ratio as high as possible. This is because if this ratio is larger, that means our on current is larger and our off current is smaller. So which is a combination of these 2 performance index. So in the lots of the new generation of transistor, we are actually focused on trying to fabricate the transistor that have the larger on-off ratio as possible as we can. So that's why we will start have the furthermore a little bit complicated design transistor, but in the end it's not that difficult to understand why, because the purpose is now we want to reduce off-state leak current. At the meantime, we hope to increase or at least to keep our ion. So to maintain the on-off ratio or to increase the on-off ratio is sometimes we call the electrostatic. The reason we call it electrostatic is because of we want to have the way to control the electrode potential here, because the reason why I have the tunneling is because of we lose control of the potential, we lose control electric field we lose control of the carrier here. So therefore, we want to have a better electrostatic improvement. And there are several strategies. The first one is very well known, that's what we call the silicon on insulator. The idea is also very simple. If we know this is a typical MOSFET, as we know, so we have the N+, and we have the dielectric, we have our gate metal. So as we already illustrate that one of the main reasons for high off-state lead current is because we have the carriers tunnel through the substrate and reach to the source side. So that's why we have the high off-state lead current. And the most simple way try to eliminate this off-state lead current is just we replace the substrate. This is usually we call as a conducting substrate. The conducting means that this is a material that has the electron and hole can be conducting. So that's what we call the conducting substrate. But if we can replace this conducting substrate as an insulator, so if we can replace our substrate as an insulator, then ideally we can eliminate the issue of the lead current conducting in the substrate, because nowadays you have insulating substrate. So as you know, the basic definition for the insulator is that the insulator have a very high resistivity, very low conductivity. So ideally, you have no chance that the carrier, the electron hole can be flow in the insulator. So if we can replace the insulator substrate as an insulator, then we should be able to reduce the off lead current. So that's the purpose why we first to consider as a SOI. And of course, there are still some problem for the SOI. That's why the SOI can be only used for the certain technology, but it cannot fully dominating all kinds of technology. And therefore, there's another proposal that we call the FinFET here. So the ideas for FinFET is based on the tri-gate structure that where we will describe later. And then also, the very aggressive version of FinFET becomes the network Y. So now you can see, we all know that this is our drain, this is our source side. The problem is that our gate are really far away from our substrate, right? So we have to mention the reason why we are not able to control the offset lead current is because our gate are far away from our substrate side. So how about if we can make the surrounding gate, that's what we call the network Y, where this is our substrate, and we have a source and drain. But now this is our channel region. This is channel region. But if we are possibly to make the transistor that our gate can fully wrap our channel, imagine as a 3D wave. So then you can have a gate fully cover all of your channel, and that can also address the issue that we can reduce the leakage current here. So that's what we call the network Y, or in the end sometimes we call the gate all around, because you have the gate all around of your channel region. So that's why we call the gate all around. So here we spend a little bit more time to explain the FinFET. So as you know, or if you don't know, it's fine. Then let me just introduce. So FinFET is basically a structure that proposed by the Professor Tian-Li in the UC Berkeley, and at the moment, also in the 1999 and 1998, the whole semiconductor industry and academics try to find a solution to overcome the off-state leak current issue. So, like I say, this is a typical, this kind of a transistor we call the planar transistor because of the source and drain and gate are all in the same plane. So that's what we call the planar FET. So in this case, we apply the gate bias, we apply the drain bias, and once our gate bias is increased larger than our threshold voltage, then we start to have the electrons formation under the gate region, which is the channel region. And because we have the drain bias here, so then the electron will be attracted from the source to drain, become the drain current. So that's a general idea of operation for a MOSFET, a planar MOSFET. But now if you look at the FinFET, so this is a structure of a FinFET. So in the case of FinFET, the general idea are more or less the same. We have the source region, we have the drain region, and then we also will apply the gate. But now the gate is not only cover the top, it's not only cover the top of our semiconductor. This top is very similar to here, but actually now you have the gate cover vertically of our channel in this place, and also we have the gate cover vertically in this place here. So now you can imagine that this is the transistor that has electron flow from the top. So this is very similar to our planar MOSFET, but also we have electron flow from sidewall. So here is a sidewall. We also have the electron flow. This is also the sidewall. So it's become the three-dimensional. So you have the current flow in the top channel, but you also have a current flow in the sidewall channel here. So in this case, our gate, original in our planar FET, gate can only control this region, and we lose control in the bottom. So that's why we face the off-state leak current issue. But now, in terms of FinFET, we can control the top channel, the service channel for sure. But in the meantime, we can also control the sidewall channel. So that gives us a better control capability of our channel in terms of the top and sidewall. So that also gives us a better on-off ratio here. So that's ideas of our FinFET structure. And in sometimes also FinFET will combine with our SOI. So you can see we still face the issue that the gate cannot control the bottom channel. So one possibility just combine with the silicon insulator. So now if we also put this place as an insulator, then we can also eliminate the substrate leak current. So now this is idea for FinFET. So if you look at the evolution from the planar FET to the FinFET, actually our idea is we just want to have the way to control the region that we cannot control before. As being the engineers like us, we always want everything can be manageable, everything can be precisely expect. So if we lose the control here, that means we lose the management capability of this region, and we also cannot expect what happened here. So that's why we come up with this FinFET structure that we can have the gate covered in 3 dimensions that have the better leakage current control capability. Okay, so now we look at this is also the left hand. This is also pretty like the clearly schematic that now our current can flow from top, which is the service channel. Also, the current can flow from the sidewall channel here. So that's the idea for the FinFET here. So the FinFET was first to demonstrate in 1999. But at the moment, you can see this is not the typical transistor that I illustrate. This is actually the P MOSFET. But to talk about the P MOSFET first, is always we have to understand the why we need the P MOSFET. So if you look at the typical drain current versus gate voltage, in most of the cases, we prefer to use the N MOSFET to illustrate the many physics, try to understand device operation because it's much straightforward. So in the previous line, what I draw here is that we have the gate bias apply. Larger the threshold voltage, we start to have the current here. And in this case, it's actually what we consider as a N MOSFET. And the main conducting carrier for the MOSFET is electrons. But on the other hand, there's another type of, since we can use the electron as a conducting carrier, for sure we can also use the hole. In semiconductor, we only consider 2 types of carrier, either electron or holes. So since we can use electron, for sure we can also use holes as well. So now if we consider the holes, then actually this is a characteristic happen in the P MOSFET, where we'll apply a negative gate bias. And once the gate is negative enough, then we start to see the current increase as well. Now we consider this is a case of a P MOSFET. So this is a case for the P MOSFET now. And the main conducting carrier for the P MOSFET, which are holes. And with the combination of the N MOSFET and P MOSFET, finally we can realize the CMOS, which is an important block for the logic operation. So we will talk about later. But this just for you to understand why in the 1999, the first FinFET paper has a characteristic like in this way, because the first FinFET was fabricated on fabricated as a P-type MOSFET here. So now we apply the negative gate bias up to certain voltage here. We start to see the current increase here, and there's some important facts related to this transistor. The first one is the R side thickness, only 2.7 nanometers. So you can see up to 1999, the very advanced understanding and development for the semiconductor is already can achieve the 2.7 nanometer of dielectric thickness. And this is on doped body. And then the last very important characteristic, which is substrate slope. So the substrate slope is a calculation mainly to estimate the slope that the transistor start to turn on in this transition region here. And this is generally we call as a substrate slope. So that's we call as a substrate slope, which is 69 millivolt per decade, which is very good. Even nowadays, look at the commercial product, probably still around 70 to sometimes below 60. It depends on the different technology. But now, if you look at, so now we know that the key performance index for a very advanced transistor. So this is a figure published in 1999. So now if you look at the last time we have mentioned the TSMC 5 nanometer technologies, I hope you can get familiar with this curve, because you can see the curve are everything are the same. This is just a combination of N phase plus P phase, and then the key index list in these figures the same. What we care about is always swing. This is swing. So now you can see from 1999 we can already achieve the 69 millimole per decade, but nowadays we can still achieve around 68 millivolt per decade. But for sure, it doesn't mean that nowadays technology is pretty lag behind the 1999. But this is the important figure of merit that in the meantime, we increase our on current, but also we decrease our off current, but also we can keep our swing in the very low. That's only 68 millivolt per decade in the case with 5 nanometer technology, because usually once we do the scaling, we always suffer a lot of the high leach current. So it's very complicated, difficult to keep the SS as low as possible. But this is just an idea that I think this is the fourth slide. So in the introduction 2 weeks ago, in the fourth slide, I already mentioned that this is a key characteristic that we will look around over again. So now you can see this is exactly the figure that the same figure illustrated again in the 1999 paper. Okay. Of course, we will still try to, as being the academics, we are always try to look at some solutions beyond FinFET. The things what we are done in the academics in the end is all possible become practical in the industry. So actually we can consider our Earth as a pathfinding for the all future commercial products here. So in this line, this line lists lots of the options beyond FinFET. And each one actually take a very, very long time from the exploration, research, development, and then in the end come to the manufacturing. So that's always come at least more than 20 years of efforts here. So now we can quickly go through that what actually the option we have in the academics, and then these options that the industry are all very interested in. The first one is considered the CMOS scaling technology. So this means that we consider the scaling, electrostatic, and we keep the higher current drive, and then we try to minimize the parasitics here. So now you can understand, once we talk about electrostatics, actually what it means is of ratios here. So this is in the CMOS scaling, one of the key challenges here is that how do we continue to make our of ratio as larger as possible. So there are several possibilities. The first one is SOI, that you already know. And we have this is a horizontal gate all around narrow Y. So this is a GAA is a gate all around. And then gate all around can be divided by one as a considered as a horizontal, and one is a vertical gate all around narrow Y. And also there's an option for 3-5 germanium, and there's an option for the CNT, which is a carbon nanotube. So that's the technology that we still try to work on. And there's there's no technology which is perfect. It's always come with pros and cons here. And then in these old technologies, some of them are very promising. Some of them have the promising performance, but with difficulty for being manufacturing. Because once we come to the manufacturing, we want to make the thousands of the wafer. We want to have very good yield. We want to have a very good uniformity. But some of these technologies are difficult to achieve that level. And the second part is that there are some transistor technologies based on the new charge-based switching mechanism that beyond or using some beyond semiconductor materials here. For example, one of the very famous ones that we call the TFET, which is a tunneling phase. So it's based on the tunneling mechanism. So we already talk about the tunneling, which is an issue that we have the electron can just tunnel from the source to the drain side, and then which cannot control by our gate. So that's a tunneling. But in the end, some people try to turn this problem become one of the key advantages. So there's a transistor which we call the TFET, just purely rely on this tunneling mechanism. So this is promising, but also face some of the difficulties nowadays. And there's another one very famous and well-known recently that we call the negative capacitance fab. So this is based on the ferroelectric material. And also, there's a very well known for the 2D materials. So these are the new material, or sometimes combined with the new switching mechanism that give us some options beyond the FinFET. Also, there's some technologies we consider beyond the charge-based switching. So these technologies for sure are very promising, and then they don't use a very conventional charge-based mechanism. Why we call it charge-based is because if you look at how we analyze the typical MOSFET, we actually consider the electron charge. We actually consider the whole charge. We actually consider how to turn on and turn off the charge. So that's we call the charge-based switching in the MOSFET device. But these technologies beyond the charge-based switching, that means actually all these technology probably doesn't need the gate bias. Sometimes by using the magnetic rather than the voltage, rather than electric field. But the problem is that if this is not a voltage drive technology, this is not a voltage control technology. So once one of these technology become the mainstream in the product, that also will dramatically different from CMOS logic. That means our circuit design needs to completely redesign again, because now the circuit is not based on the voltage drive. It's based on the new switching mechanism. For example, once we talk about the spin logic, which is mainly based on the magnetic field. And we also have the very well known and promising for the quantum computing. So these are actually also based on the new operation, which involves more complex physics, but sometimes didn't rely on the conventional voltage charge, this kind of switching. But this technology might also need a lot of effort of the new circuit designs. So in the end, if you try to look at the no matter for the scaling or no matter for the application need, you always very often to hear about the term that we call the low power consumption. So one of the goal when we develop the transistor is we want to have the low power consumption. But in terms of the electrical characteristic, what does really mean for the low power consumption? So in the left hand figure is a typical MOSFET. So now I think everyone are very familiar with the general operation for the MOSFET. So inside the MOSFET, we actually very interested in to understanding the drain current versus gate voltage. Especially sometimes we would like to understand the log ID versus the VG. So imagine if now we have the characteristic, something like this one. So this is a very general ID-VG characteristic. And we want to this device operate in our targeting current, which is this. So the spec for our product is that we hope this transistor can deliver such level of the current here. To deliver such level of current, this transistor need to bias, for example, 1.5 volt. So that's a typical why we have to have to make it a high performance transistor, because in the end we want this transistor to deliver the current that fit our product needs. But if nowadays we can try to fabricate another transistor with very similar of steady current, but can turn on faster. So that means if you look at this is a critical performance that we call as a substrate slope. For example, the blue one might have the SS around 90 millivolt per decade. But if we can try to fabricate the transistor that has a lower substrate slope here. So lower substrate slope, that means our device current can turn on faster. So we have the steeper slope than here. In this case, we actually no need to operate 1.5 volt to deliver such current. Based on this curve, we can expect we only need to operate at 1 volt, but we can have the same output current. So that's actually gives us a way toward the lower power consumption, because now we reduce our operating voltage from 1.5 volt to 1 volt. So that's why we care so much about the substrate slope. We care so much about on current, because in the end we can use a smaller voltage, but it can give us a same or even higher current, which is good for our product here. So now we can all realize that once we can make the transistor has a lower substrate slope, which is good to reduce our operating voltage. And in the end, which is good for the low power consumption. Because now we only need to operate at 1 volt, which is good for low power operation as well. So that's the general idea that how we try to make the low power operation a transistor. And basic idea is we will try to have the substrate slope as lower as possible, and in that case we can operate in the low bias but reach the same or even higher drain current. Okay, so our technology not only, when we talk about semiconductor technology, we are not only consider the scaling. If we look at the full picture for the whole semiconductor roadmap, actually there's a one for sure that you hear very often, which is we try to have the scaling down to 22, down to 14, down to 7. And nowadays, we try to have a 3 nanometer. So this is a technology that we generally call the more. So to enable the more technology, what we try to have is the scaling. So this is a technology try to fit the Moore's law. But actually, there's a part of the technology didn't have to follow the Moore's law. These technologies mainly to interacting with the people and environment, and this is the technology we call the more than more. So in the case of more than more, when we develop this technology for our application, for our the human need, but it doesn't really have to follow the scaling, doesn't have to follow the Moore's law. For example, we have this RF, which is nowadays we have the 5G and 6G technology, and this technology doesn't have to follow the Moore's law and doesn't have to be scaling. Of course, scaling also brings some benefit, but it's not the very hard requirement. And also we have the technology called the power, which is nowadays very often being used for the charger or even for the electrical vehicle. And also we have a technology for the sensors, for the biochip. So these all can be considered as a technology that permanently interact with the people and environment, and that's we call as a more than more. And in here I show the one that I'm most familiar with related to the more than more, which is the power electronics that's related to the high power technology. So this is a schematic that actually we have the electricity coming from the power station through this high voltage transmission, in the end come to our digital chip. So now we all know for the low power operation, what we explained before is we try to have as lower as a power that our digital chip can operate, which can be 1 volt. As we already previously, IDVG already mentioned that we can try to make it the transistors that have the 1 volt operation, but with a very good on current here. So usually when come to our digital chip, we try to have a lower voltage as possible as we can. In this case, which is 1 volt. But in reality, once we have a power supply from a power station through the high voltage transmission, actually there are so many power converters need to be done during this transmission. So for example, first of all, we have the around more than 13.k kilovolt AC voltage, and we have the first stage is we try to transform to the 200 volt AC, and we transform to the 400 volt DC, and start to down to the 48 volt and 12 volt and down to 1 volt here. And the reason is that we don't have the transistor that can immediately transform from such high down to such low. So we need to have a several stage of a different voltage conversion that's involved for the AC to DC, DC to DC, and in the end DC to DC. But the problem is that each voltage conversion, each power conversion, we always lose something because it always involves the non-perfect efficiency. So we have the 98% efficiency, we have the 95, we have the 85%. So in the end, the overall, if we try to have the voltage power delivered from the power station to our digital chip, we actually can only achieve the 85%, which we have a 50% efficiency lost during this voltage conversion. But if we try to replace the technology with some new material, for example, in the case here I mentioned is a gallium nitride based solution. So now traditionally we need to have a two stage. We have a 28 volt to, this is 28 to 12, and this is 12 to 1 volt. But now we can replace this two stage converter down to only one stage, which is 48 volt to 1 volt. but with higher efficiency and higher output power. So this is the thing that why you can have something like the technology that enable to save the energy. And nowadays, this server power architecture is pretty important, especially the demanding for our AI server. The power to drive our AI server is dramatically increased. That's why you have already heard about that lots of the data center that really need a very good facility to provide the electricity, and then even some of the big giant like Google, Facebook, they consider to build up their small nuclear plants to try to have enough electricity. But also, if we can use a wide bandgap material and technologies, that can also help us to meet the need for AI server power demanding. So this is one technology that in the case of the modern mode. In general, this is the technology. As long as we talk about the voltage, power is always in the domain of what we call the power electronics. So power electronics is not only considered that you might already use as a charger. So the charger is one of the example of a power electronics, as nowadays you have the phase charger. But also the power electronics involve all kinds of the technologies that need to convert the energy, which is automotive. So that's why we have the electrical vehicle car, because that also needs a lot of the power electronics to help us. So by using the new semiconductor material, that actually we have some of the additional benefits that are beyond your imagination. So this is one of a very successful example. This is a literature coming from the 2014. So you can see at the moment it's already the demonstration of this is silicon device operating 200 volt. But now if we replace silicon device to gallium nitride device, where we can highly reduce the size. And where is our gallium nitride? Hence, device is here. This is very small one. This is our gallium nitride transistor. So by using the gallium nitride transistor, that's why we can have the very smaller and then the faster laptop adapter. So this is the first concept demonstration in the 2014 in one of the conference to demonstrate that the conventional laptop adapter to become this kind of a laptop adapter that's smaller, the same like your cell phone adapter. So now this is also one of the example to remind everyone that what you have been done here actually are all very valuable, because in the probably 5 years, 10 years, one of your works can become really the product that can influence the society. So this is an example. In 2014, nobody really believed that we can make the charger that smaller, faster than the conventional charger. But nowadays, it's very easy to buy this charger in the market, and you all already enjoy this smaller and faster charger. So in the end, when we consider the semiconductor innovation, if we try to have the energy efficient electronics, the energy efficient, it means that what we want to fabricate the low power operation, low power consumption technology, or we want to have very high efficient power converter. This kind of technology in the end is all related to the power because the power is related to energy. You always want to have the energy that can have very good efficiency. Then we don't waste a lot of energy, but we can use a little amount of energy and power still try to drive our applications. Okay, so here just start to go through some of the up-to-date advancement in our semiconductor industry. So this is a slide coming from the TSMC in 2024. This is a slide coming from the TSMC very senior director and focus on research, and who present the process technology evolution in the one of the key events that we call the IMEC Technology Forum, ITF, in Taiwan in 2024. So this slide is actually this picture is very informative. So we can see from the 2021, from the 28 nanometer, we start to enable the high K and metal gate. And then we start have the several innovation to enable our transistor can follow the Moore's law for sure. First, we move from the planar to the FinFET. And the FinFET will keep up to the N3 or even the N2. And then further beyond, we start to have this nano chip here. And in here, you can see there's many different technologies to enable our new transistor. So we have as I say, high K metal gate. We have the strand silicon. This is something that we also have been mentioned. We have the high mobility channel. We have the EUV. These are also very well known in the news. And then beyond the N4 and N3, so we have the different FinFET, self-aligned, low K, and even the low resistance back online technology. And then we have this nano flex, and then also we have the backside powering. So in here, we won't talk detail for each one, because each one is take like more than 10 years, 20 years research in this become the technology that enable a new product. But this just let you know that our semiconductor is still moving. We still have the very fantastic process and technology being developed now. And then also, for sure, we from the immersion, in the end, become the EUV. I think the EUV, everyone look at the EUV online, you will find out lots of the detailed explanation that how EUV is important for semiconductor technology. So this is 2024, but then we back to the literature that reporting the 2019 is already discussed as several device option summary here. So we have the FinFET for sure. So still in the production. It's already in the production, but we still start to have the nano chip, nano 1, germanium 2D, and CNT. So I think that if we really follow the semiconductor development history, probably for you, it's the first time to heard about 2D or CNT. But if you follow being while, you will find that this is not always a new thing anymore. So since 2019, it's already start to be in research and even be in the development. And also, if you look at the potential roadmap till the 2036, so this is roadmap provided by the IMEC. So already mentioned that what else beyond the FinFET? Of course, we have all very fancy technology, 2D quantum computing, but that's probably take more than 10 or 20 years to fully realize. So we need to have the technology that enable in our current platform. So beyond FinFET, we start to have the gate-all-around nano chip. This is a gate-all-around nano chip, and then we have a fork chip. And now, recently, it's very promising is what we call the CFET here. So CFET is actually the stacking of the NMOS and PMOS, which we will talk about later. So that based on CFET, so we can have the technology further beyond the gate all around and beyond the FinFET. And also this kind of the CFET or the new technology actually has been already mentioned in the lots of the different places. So this is the same in the TSMC also mentioned that now the main technology is still probably around here, and the next generation could be either nanosheet or CFET. So that's the options right now that industry try to realize. Of course, we have some very advanced material like a 2D or CNT can be also considered in the future. So here is a CFET. So as already said that to enable the logic operation, we need to have the inverter, and which inverter will basically inverter is a combination of the that's we call CMOS, which we have the P MOSFET plus the N MOSFET. So with a combination of PMOS and NMOS, that's what we call CMOS. Once we have a CMOS, this kind of architecture, then we can realize the logic function, especially the inverter function. What does mean the inverter? Inverter, it means that if we apply the signal 0 here, then the output here becomes the 1. If we apply the signal 1 here, the output signal will become 0. So this is the basic the inverter function in the logic. So that's why this CMOS we should call as an inverter here. We will talk. We will explain why it has a 0 to 1 or 1 to 0 later. But the idea is very simple. But in here we can see tradition. If we want to make the CMOS, we need to have the NMOS and PMOS on the same plane, side by side with each other. But the problem is that we need have this kind of area. You know, in terms of the very advanced semiconductor, the size does matter because size is always related to cost. The chip size is always related to the cost. So if we can try to stack in NMOS and PMOS together vertically, so that's we call the CFET here. So this is why the CFET is very promising at this moment because of we can save the chip size, so we can try to stack in the NMOS and PMOS together, and then we save the chip size. We can have more higher density. So this is the idea that we call the CFET technology. So based on what TSMC says that the vertically stacked CMOS architecture provide around 1.5 up to 2 times higher density than the planar CMOS. And this is the first, not the first demonstration, but this is one of the demonstration from the TSMC. This is in the 2023 IEDM, and then this is a complementary CFET demonstration at a 48 nanometer gate pitch for the future logic scaling. So now you see, if you see the right hand figure, probably you should not afraid this analyze the right hand figure anymore, because this is exactly the same that we have already mentioned. So in this is a drain current versus gate voltage here, and then this is substantial slope. So they demonstrate that it is possible to stack the N FET on top of P FET, but with a very good substantial slope. So that's a demonstration of the C FET. Okay, so that's the end of the introduction here. So we will take a break for 10 minutes and then come back for the start to move on a little bit more fundamental that we will explain first for the materials and then the introduction. And then one more thing, just want to mention that I mainly upload the notice slide and also the video in the Facebook. So you need to, I think lots of people you already joined. But I'm not sure that I approve everyone. And some of you might start to join the class today. So you need to join this Facebook to get the latest information and some of the announcement. But if you already apply it and then I didn't approve it, just let me know. I will approve later. Okay, so we'll take a break and then we'll come back in the 10 minutes later.
我想问，就是为什么有时候会看到 S ring 嘛，就是萎缩的时候，
对，
好像会常看到 S ring，为什么？
因为他们会用 S ring
当
来做一个
指标
评估的平台，就是先 demo 一个，就是我觉得应该是他把这个 S ring 当成一个 technology 做完之后去评估的一个 set 一个测试的这个类似小电路，对，所以很多会用 S ring 来当做一个，因为你这个整个这个技术，就是以台积电来说的话，它也很难确定客户会下什么电路，所以它需要一个很 general 的这个电路，就是可以去跟每个 technology 去做比较。对，如果你去 demo 很复杂的电路，那它没办法跟前一代或是跟别人的技术去比较。对，而且 S ring 也很 care 这个面积跟 density，所以会 S ring cell 会变成一个很 general 的一个测试这个 technology， 对，一个测试这个 technology 的好坏，然后但是它又比较到达一个电路跟系统的指标性，对。
MOSFET，
对，
我之前修过 现在有在修实验课，然后他有在讲说 ，MOSFET 它其实是4端元件。
对。
那
因为我们的通常是 substrate，因为
substrate
跟我这画的是简单示意图，但通常 substrate 也可以加 bias，substrate 也可以加 bias。
为什么通常我们会把 substrate 跟 strain 跟 source？
因为我们要减少这个元件操作的复杂度。但有些情况下，有些人会在 substrate 加 bias，但通常我们比较不希望，因为我们希望把这2帮的讯号都光在一起的话，你就只要考虑 gate 跟 drain bias 就好。如果你又让这个的 bias 跟 source 不一样的话，你这边就会产生压差，那你就要更多更复杂的考量。
那这会应用在什么地方？它有什么作用？还是
你加不同的 substrate 的话，你就可以调它的 VTH 啊。对，然后在有些情况下就是一定会不一样。对，这只能就是蛮 depends 这个电路的应用。对。但是通常来说，我们会比较希望就是这2端会把它绑在一起，这样可以减少很多。
记的，
对，因为你这边是 N plus， 这边 P， 所以你这边就有多一个 NP 界面。对。
了解。像这个地方啊，
对，
为什么这明明看起来比较斜？
对，
为什么是70？然后这明明看起来比较没有那么斜。
因为它这个你要算它的，你要看它那个 substrate load 的定义。对 ，substrate 定义的话它是电流跟这个电压，所以它是这个越小，它的斜率越小。到时候我们最后会讲那个 substrate load 的数学公式。
现在只是先告诉我们说，如果
所以为什么大家就要最小越小其实带着就越斜。对，
了解。
对，
谢谢老师。
好。How is going?
I really haven't about that. Right now, I'm really confused about it.
So the Tian-Li contact you. So now it's yeah. So did he contact you?
Yeah.
And then did you start to perform some basic?
Yes, but I'm still a little bit confused. So yeah, just try to lead his effort.
I think the first day is that I will talk to him later, but I think the first day will be he try to guide you to let you be familiar with the testing machine and you can operate. At first, most important because if you try to look at the literature to understand the device that you are characterized, I think you'll get more confused because that's way beyond the knowledge you have. But for usually the undergraduate project, at least I want you to have some hands-on experience in how to do the testing, how to apply the curve, how to really see the semiconductor chip. Because all this knowledge later, if you are, I think you already measured the IDVG, right?
I mean, like we did last time, but the program crashed. So kind of measured like one time.
Yes.
But like the program crashed.
Okay.
Last time.
Okay.
I know that we're going to measure it, but like.
And do you come to did he help you to reserve the time like every week in the week? Okay. In the beginning, it always takes some time, but I will check with her about the status, and then delay let you know that we have the weekly meeting. Undergraduate probably will resume very soon on the Thursday. Usually it's 12:30.
Not yet.
Because it has been cancelled for a while due to Lunar New Year, and now they also have to wait everyone to finalize their course schedule. But ideally, it should be the 12:30, but it's online, so it's online. You don't have to come, just online, and then it's a take turn. Everyone, not you have to report every week, but just everyone will report, and you can understand what other undergraduates doing as well, and then you can also start to get familiar with the how to make the presentation, how to summarize it. And sometimes it's just very simple, just plot some IV curve. Yes, I will talk to Tian-Li. Okay.
OK， 味道老师的签名啊，来都给他签名。
还是你都在自己？
他这个接地，没有吧？他那接地干嘛？我回家的时候找不到，我说应该在宿舍。那我在宿舍的时候找到，我说应该在学校，那就在学校找不到。
那个是
他们都是应该是那个在试他尽量不在对，逼你上面是有然后下面所以他如果在这边接，然后这边接那个电子它一定是上面要的它电子系统会有上全
Okay, we will start our class, and I think we finished the class enrollment, so probably it's a good time that I can check the attendance, and also at least that I try to remember everyone as possible I can. Okay, 刘维金。林奇雅、施承谦、林玉红、卓宇腾、曹俊龙、蒋新伦、黄敬浩、陈和佳、简伟成、尹文挺、吕俊杰、詹雨桐、吴博翰、谢英珠、陈瑜杰、李新月、陈汉硕、庄伯君、沈婉平、杨展邦、许明凯、蔡少祥、黄富群、罗正浩、戈帕吉、 吴周玉、张荣麟、魏君燕、孙海明、尤伯彦、李耀宇、江信生、杜瑞慈、廖婉瑜、江正勤、刘星浩、李博勋、古宇轩、刘宏奇、柯仲远、孙正伟、黄国坤、陈印祥、魏于婷、李义儒、王新勇、黄立肯、李竹云、高守庭、吴伟庆、蔡月俊、邱训松、陈伟旭、班硕、班早 I think this is international student. Student number is 3135400024. What's your name? What's your first name? What? Ban Okay. 陈柏瑞、陈新威、刘嘉诚、毛家俊、郭俊佑、林佑哲、常佩杰、林伟彤、郭子佑、邓有福、穆海曼 Student number 4135400007. 刘桂红、何新品、王义照、洪敏祥、黄怡珍、林冠浩、范廷伟、吴雅静、林明杰、邱元杰、黄庭勋、林承志。OK。 Okay, so now we move to the chapter 2. So now we will start to go to the very fundamental side, first to understand the materials introduction and then crystal structure of the solids. So in this chapter, we mainly talk about the basic materials that we can use for the semiconductor and how these materials look like in terms of the crystal structure. So first of all, you have to understand that what actually the semiconductor device architectures and how to form the semiconductor device. If you look at the semiconductor device, it's basically a combination of the 3 different pillars. The first one is materials. And then the second one is a junction. And the last one is a device. So in terms of materials, that's we basically know that we in the semiconductor we can either have the piece of the material which has a different doping in the end. For example, we have the N type. We can also have the piece of a material which is a P type, and the N type means that we have this is a material that has a majority of the electrons, and then the P type is the material has a majority of the holes. But now, if we try to put these 2 different doping material together, and then we will form the junction in between these P and N. Which is P, N. So we can form this. We put these 2 different semiconductor material together, and then once we put together, the most interesting part, which will be the interface between these 2 materials, and that's we call as a junction. So therefore, in lots of cases, to understand the semiconductor operation, we always first to look at what happened inside this junction. And then once we understand the junction, finally, we can consider the whole device, which is consider the overall of these 2 different materials. That's we call as a junction, a device. That's what we call as a device here. So basically, we need to, once we consider semiconductor device, we have to first to consider what kind of materials, and if the material has a different type of property, and once we put together, and most interesting and critical part, which would be the interface, or we call the junction here. And once we understand the junction, we can finally to consider the whole, these 2 materials as one piece of the device, and then we can understand the device characteristic. So by understanding the basic, the PN junction and PN device, that's already very useful for us to understand the whole semiconductor device, especially for the MOSFET. So in the case of MOSFET, So now we all know that in the MOSFET we have a certain substrate, for example, the P-type substrate. And on top of P-type substrate, we have the source and drain here, which is N plus. And then on top of the substrate, we have the dielectric. We have a dielectric, which is silicon dioxide. And also, we have the gate. We have the gate metal on top. And so this is a basic structure for the MOSFET. And the reason why I have to draw this is because I want to illustrate that the understanding of the PN junction is very crucial as well to understand the MOSFET. And that's why that in all of the semiconductor textbook, we always begin with the PN junction and move on to the PN diode. And later we talk about the MOSFET. Because if you try to look at this schematic in detail, you will find out that this is actually the one place we might start to have the N and P material. And this is another place that we have the materials that combine the N and P. So therefore, this region is we have the PN junction. And then the left hand side, we also have the PN junction here. So that's why we're always starting from understanding PN junction, because in the end, the understanding of PN junction can help us to understand lots of the parasitic effect, non-ideal effect in the MOSFET. Later, we will also talk about this. Okay, so now first we have to understand the materials. So in terms of materials, as we all know, that we can look at the chemical species in the periodic table, and then in the column 4, where we have the carbon, silicon, and germanium. And this we consider as a elemental semiconductor. Elemental semiconductor, so that's a material that only has one single piece of the atoms. For example, we have a semiconductor that can only constructed with silicon material. So that's we consider this is a elemental semiconductor. So that's found in group 4 inside the periodic table. And these elemental semiconductors are composed of the single species of the atoms, and the most often we use nowadays is silicon and germanium. So in the silicon and germanium, we can consider this is an elemental semiconductor here. And then also on the other hand, we can also have the semiconductor material that combine with the 2 different species here. And therefore, the most often considered is a combination of a group 3 and group 5. So that's we call as a compound semiconductor. That's what we call the compound semiconductor. So in the case of a compound semiconductor, we very often use is, for example, the gallium, the indium, and then the phosphorus, and then the arsenic. So by combine these two different species, we can have the compound semiconductor. For example, the gallium arsenide, the indium phosphide. So that's we usually call as a compound semiconductor. So the compound semiconductor are formed from a spatial combination of group 3 and group 5 elements. And this can be considered the two elements, sometimes we call the binary compound. For example, the gallium arsenide or gallium phosphide. These are the two element compound. Or sometimes we can have the 3 elements compound. For example, the aluminum gallium arsenide. So these are 3 element compound. Or another very well-known one is aluminum gallium nitride. So in the case of the 3 element compound, we can also have a different contents percentage in terms of aluminum or gallium. For example, we can have the 20% aluminum, we can have the 80% gallium, or we can have the 20% aluminum and then the 80% of the gallium nitride. So that's why you very often to see in the literature of we actually not only call as aluminum gallium nitride, it's aluminum 0.2, gallium 0.8, and nitride. And this is because we have the 20% aluminum, 80% of gallium. And the good way for these 3 element compound is we can adjust the content of aluminum and gallium, and then we can start to change the material. So that gives us to change the material property. So that gives us the flexibility to design the material fit our device needs. So this is elemental semiconductor. So the germanium is the first material used in the integrated circuit, and then it's a trace material. And germanium usually have the property of a small band gap. And also the poor thermal stability. And also the gallium arsenide is soluble in the water. So because of the property of very poor thermal stability, and also the gallium arsenide is not very stable under the humidity because it's soluble in the water. That's why, although the germanium is the first material that discovered can be used in semiconductor, but afterwards, people do not consider germanium as a main material anymore. However, they consider silicon, because of silicon is one of the most common elements. In the world, so not like germanium. Germanium is a trace material, so that's not difficult to find, but the silicon is easily to have it. And also, the band gap is larger than silicon, than germanium. So the silicon band gap is 1.1 electron volt. And also, the very important feature for silicon is that we can have very stable silicon dioxide. So, we consider all these properties. That's why the silicon is become the main dominating material for semiconductor, because it's one of the common elements in the world, so it's easy to have it. And the silicon has a large band gap, and we will later talk about what does the band gap mean. But sometimes the larger is always better than the small, because germanium is band gap is way too small. And also very important is that we need to have very stable dielectric. As you know that in the MOSFET, one of the key inside the MOSFET, one of the key elements is that we need to have very good dielectric, and silicon dioxide can be used as a very good dielectric. But however, silicon still have one drawback, which is indirect bandgap material. And then the indirect bandgap material that will make the silicon is not suitable for the light emitting application, LED. So you know the LED is the semiconductor that can emit the light, but usually the LED needs the semiconductor has a direct bandgap. But unfortunately, silicon is an indirect bandgap, so has a very poor efficiency for this light emission. That's why you never heard about people use the silicon as a LED material. But although there's a small little drawback, but the other three properties already make the silicon as the most stronger semiconductor material that can be used even in the past, nowadays, also in the future as well. And this is a schematic for the TSMC 16 nanometer FinFET device. And the dielectric SiO2 is here. So the SiO2 is here, so you can see that it's clearly that we need to have very good dielectric that can be used for the MOSFET structure or even for FinFET, and this dielectric need to be very stable. And the evolution for the transistor that had already been reviewed in the first chapter in the introduction. In here, just quickly go through again. So we have the planar, which is a MOSFET, and then we have the fully SOI. That's usually we call as a FDSOI, which is a fully depleted SOI. So this is SOI. This is insulator. And also, the most advanced one is the FinFET. And in terms of the compound semiconductor, there are some very unique property. For example, the first one, the 3,5 material that we consider the first is gallium arsenide. So gallium arsenide is direct bandgap. And also, gallium arsenide can be used as considered as a property that has a high electron mobility. So that's why the gallium arsenide has been already used in the lots of communication and cell phone application, because it has a property with the very good, the high electron mobility, so can be operated at high speed, which is very good for the communication application. So if you look at this is one literature, just want to show that also one of the examples that the research work on for a really long time, it then become the product that we use in our daily life here. So the title is gallium arsenide base heterojunction bipolar transistor for very high performance electronic circuit. And this is a paper published in 1993, but nowadays we still use gallium arsenide as a low power RF technology in our cell phone, because it has advantage which has high mobility that can enable for the high speed application. And one thing I want to particularly illustrate that if you look at the co-author of this paper, there will be the one name that you might hear about, but once you join the NYCU, he is our ex-president, so it's not no more in the NYCU. He's back to UCLA. So this is our previous president, Professor Frank Chen. So that's why he has been involved for this communication technology in the very early time, from the 1993, which he worked on the gallium arsenide based technology. So this is just an interesting fact that I share to you. And also, in addition to the gallium arsenide, now we also have another very well-known compound 3,5 material that we call the gallium nitride. So gallium nitride has some special property. First one, gallium nitride is a material that has a direct band gap. So the direct band gap material, which is very suitable for the LED application. So now if you look at all of the LED-based electronics in our daily life, it's all enabled by the gallium nitride material. And even the inventor related to the LED, who in the end was winning the Nobel Prize because of he tried to adapt the game for the LED, and in the end, because of his actually it's a 3 professor from Japan. In the end, because of this first adaptation to try to realize the game for the LED, that makes them to win the Nobel Prize. And also the gallium nitride has a very good property in terms of as well high electron mobility. And the last also is one of the most key feature for gallium nitride is that gallium nitride has a large band gap. Has the large band gap, which is 3.4 electron volts here. And we will talk about that what would be the advantage that the semiconductor material has a large band gap. And not only the 3-5 can be used as a compound, actually the group 4 material with a combination of the silicon and carbon, that we in the end have the compound material that we call silicon carbide, can be also considered as a compound. And silicon carbide has also the properties of large band gap. And also very good thermal conductivity. Very good thermal conductivity. So that's a basic but a very unique feature for the gallium arsenide, gallium nitride, and also the silicon carbide. And one of the interesting application, if the material has a large band gap and good thermal conductivity. So if we try to use a material that has a large band gap and good thermal conductivity, large band gap and good thermal conductivity, that also indicates this electronics based on the material has a large band gap, good thermal conductivity. That means this electronic is very suitable for the high temperature application. So, for example, actually the different electronics has a different targeting operating temperature for the different environment. If you look at the electronics that most close to us is usually we call as the consumer electronics. So the consumer electronics is the typical cell phone, laptop, all the electronics that we use for daily life. And then the maximum operating temperature requirement for consumer electronics is around 125 Celsius degree. So usually we will test onto 125 and we will go further beyond. But for some different application, we have a different temperature requirement. For example, the automotive electronics. For the case of automotive electronics, this is the electronics that will be installed in our car, installed in our electrical vehicle. So usually we want these electronics can sustain a relatively high temperature. So the requirement for the automotive electronics needs to be stable up to 200 Celsius degree. In addition to this one, we also have very special one that we call the space electronics. So space electronics, for sure, based on the name, then you will realize this is a technology we are using in the space. No matter for the satellite, for the some like the exploration vehicle in the different planet. So this is what we call the space electronics. But inside the space electronics, because of the planets like Earth, that we can have the regular temperature below 40, but some of the planets might have the temperature up to 300, 400, even 500 Celsius degree. So in the case of space electronics, the requirement is we need to make sure our semiconductor technology are also very stable in the relative high temperature, and especially this is target for the space application. So the electronics need to be very stable, more than 300 Celsius degree. So if you look at the NASA website, actually in their website, there's a dedicated page talk about NASA how to use the silicon carbide technology for the space application. And they demonstrate silicon carbide electronics, not only for power, even for logic, for whatever, because this is going to be installed in the spaceship, in the satellite. So they actually demonstrate the silicon carbide technology can be operate more than 500 Celsius degree. So that's why with a material that has a large band gap and good thermal conductivity, this is a material that is ideal for the space application. Now we look at what does it mean for the band gap. The band gap actually is a definition between the conduction band, the bottom of a conduction band, and also the top of the valence band. The idea is that once we talk about the quantum mechanics later, we will start to talk about the quantize. So then we will start to have the discrete energy level, and then later on we will define the conduction band and then the valence band. And the difference between the conduction band and then the valence band is something we call the band gap. So in the case of silicon, we have a band gap for 1.1 electron volt. You can forget the band gap for the other material, but you definitely need to remember the band gap for silicon, because we always use a 1.1 electron volt as a reference to look at the other material has a large or smaller band gap. For example, in the case of germanium, only have the around 0.67 electron volt, which we consider the small band gap, because the small band gap is because we compare with the silicon. So this is a small band gap. But on the other hand, if you consider the material that has a larger band gap than silicon, this all the material we consider, once their band gap value is larger than silicon, we all consider this is a larger band gap. Or sometimes we call this as a wide band gap semiconductor. That includes, for example, silicon carbide, gallium nitride, and even the diamonds here. Diamond can be also used as a semiconductor material as well, because it has a very large band gap, but it still can be conducting, have the electron holes conducting in the diamonds. And one of the key implication for the band gap is related to the leakage current. So in the further explanation, in the later part of course, we will explain that actually what does mean the valence band and conduction band. But in a very small, very short summary, is that the electrons are full below the valence band, and then the region beyond the conduction band is empty. So that means if we want to have the current flow, the electron need to cross the band gap and reach to the conduction band. In the end, will become the current. So that's a easy and the most important implication for the band gap is this region are full of the electron. This region is empty, and therefore the electrons will try to cross the band gap and reach to the conduction band, and this will become the current. Now you can start to foresee the smaller band gap. That means electrons are more easily to jump across this region and reach to the other side. So therefore, we can always expect the smaller band gap. That always means the higher leakage current. On the other hand, once we consider the extremely case where we have a very, very large band gap and the electrons are full inside the valence band, but because of this very large band gap, so the electrons are very difficult to cross this large band gap and reach to the conduction band and become the current. So that's why the large band gap always implies the low leakage current. So this is an example that how material property in the end to correlate our electrical characteristic. As you know, once you join this class, I believe that everyone here wants to become more and more toward the electrical or electronics engineering. So engineers, and then if you look at the background in the class for all of you guys, we have a student coming from the material science, physics, mechanical engineers, and so on. But one of the important things is that we always need to correlate the materials property or all of the physics and all of the fundamental things in the end with our electrical result. Because in the end, when we design our semiconductor, what we care, when we design our device, we always care the current, we always care voltage. So in the end, we hope that the materials knowledge can be correlated with our electrical characteristic, which is the most important part for us to be a good electronic or electrical engineer. Okay, so now we finished the materials. So now we move to the junction. But in terms of a junction, also we have to understand there are all kinds of different junctions. In the previous one, what we only illustrate is the case where we have one type of doping semiconductor connected to another type of doping semiconductor, and we form the junction here. So that's we generally call as a PN junction. But in reality, we can put everything in our semiconductor. It's not only limited to the one kind of doping. We can also put the metal on top of semiconductor. So then we will have the junction in between. Also, we can put completely two different kinds of semiconductor. In this case, it's mainly silicon and silicon. But we can put silicon and germanium or whatever. So we can try to put all different kinds of semiconductor together. Then we also need to understand what happened inside the junction. Or the last part is we even put a semiconductor plus insulator. So the outside is the insulator. So we put the insulator on the semiconductor. So now we also have to understand the junction in between here. And also we put the metal on top of the insulator, we also need to understand the junction. So in the end, once we understand all these different junctions, what happened inside this junction, basically we already understand what would be the device operation, what would be the device physics inside. So let's look at the one by one. The first one is the metal and semiconductor junction. So if we look at the metal and semiconductor junction, that's we call the MS junction. There are several different types of the MS junction. The first one is Schottky. So once we put the metal on top of semiconductor, we can form the one type of junction, what we call the Schottky contact. And the typical characteristic for the Schottky contact is like this one. So we have a current versus voltage. And because of once we put the metal on top of the semiconductor, you can imagine that there's something happen in between, and this happening in this region will make our IV characteristic not ideal. So typical Schottky contact exhibit the characteristic like in this way. So that means we can only have a current once our voltage is larger than certain voltage. Then we start to have the current go through this junction. This is a typical characteristic for the Schottky contact. And on the other hand, we can have another one, it's an ohmic contact. So the ohmic contact is relatively straightforward for everyone, because if you have followed the electronics or sometimes I think a high school physics, we already know there's a rule called the ohmic law. So ohmic law basically it just illustrates the same, the current versus the voltage, but because of ohmic contact and ohmic law, so it always straight and starting from the zero here. So then we can have this kind of the characteristic, or we can also have this kind of a characteristic. And the difference between the yellow and blue is the yellow one indicate the lower resistance here. So this is a typical characteristic for the ohmic contact. And this is for the Schottky contact. For sure, later once we talk about there's a dedicated chapter talk about the metal semiconductor. We will also illustrate why we will have the characteristic like in the Schottky or characteristic like in the ohmic here. And also the last one is the metal semiconductor transistor. And sometimes we call them MOSFET. And this kind of transistor is very similar to the later what we call the JFET here. But just let you know that there's one kind of transistor that even we don't need a dielectric. We just put the metal on top of semiconductor and you put the source and drain. You can still operate as a transistor. But in here, we won't talk in the detail, just for your reference here. And the metal and semiconductor, why this is crucial? Because in the end, if you look at our MOSFET. Actually, the metal and semiconductor is considered as one of the critical part inside our MOSFET structure as well. So now we back to the structure for our MOSFET. So now we all know this is a source. And we have the N plus, we have the N plus, we have the dielectric. And we have the gate metal. Gate metal and dielectric here. So this is a very simple schematic that where we have drawn before, but something actually we are missing. What I didn't draw before is that in terms of the drain and then source region, we all know we need to apply the drain bias. We need to apply the source bias. But actually, the applied bias is not directly on top of semiconductor. It's actually we have to apply the bias on top of metal. So in reality, when we fabricate the transistor, we always need to deposit the metal on top of semiconductor. We need to deposit the metal in the source region and then the drain region. So this is a metal electrode. And therefore, now you can foresee, once we put the metal on top of semiconductor, for sure, the interface in here, is a metal semiconductor junction. But in the transistor operation, because of this metal semiconductor junction, and we put the two different material together, and normally we have to consider the resistance in between. So that's is very crucial one, is what we call the contact resistance. So ideally, we always hope we can make the contact resistance as smaller as possible, because we want to reduce the voltage drop here and here. So that's why we always try our best to make the smaller contact resistance as possible as you can. And this is also one of the reminders that in the end, once we really move on to our MOSFET chapter, you will realize that understanding MOSFET is actually just a combination of the lots of a small piece, what we learn from the MS junction, what we learn from the PN junction, what we learn from the MOS. So we know we have the PN junction here. We have the MS junction here. And later we also will talk about this place. So once we finish all these small pieces and then we combine together, that's a MOSFET. Okay, so the next is the junction between the P type and N type. So this is usually we consider as a PN junction. And in reality, there are several varies when we consider the p-n junction. The first one is for sure the most basic one is the p-n diode, which p-n diode is mainly based on the p-n junction. And the second one is a bipolar junction transistor. Or we call as a BJT. So the BJT is a structure that looks like in this way. So we have the PNP, or we have the NPN. So that's what we call the BJT. And inside the BJT, we have to deal with the two junctions. So we have junctions here, 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 here. So that's why that always in the many semiconductor textbook, we always first from the p-n junction, because once we understand p-n junction, it's getting more easy for us to understand the MOSFET and BJT as well. And also, the p-n junction also existed in the one special device architecture that we call the junction FET. That's what we call the JFET. And then the JFET is a structure it's very similar to our MOSFET. We still have the source and drain here. But now we are not using the P-type substrate. Actually, we consider to use N substrate. And we try to, inside the channel region, we have the P doping here. And we apply the bias VG to modulate this p-n junction. So by control this p-n junction, we can also turn on, turn off our transistor. And we will talk about JFET in the last chapter. And also, we have the last one. It's what we call the thyristor. Thyristor is a structure that combines a p-n structure. So which is a device look like in here. P-n. And then in this case, we have 3 junctions. So in the normal semiconductor class, we won't teach the thyristor. It's a very special and dedicated structure for the very high power application. But in the course of the power semiconductor, usually we will learn the thyristor from there. But the thyristor is actually, although you will not learn in the typical semiconductor textbook, but if you are a little bit experienced in the semiconductor device, you probably already know there's a reliability issue called the ESD. So ESD is mainly related, the full name for ESD is electrostatic discharge. So it's mainly due to the triple electricity discharging, 摩擦放电. So that's a very well known and very important reliability issue for the semiconductor. So usually we need to have a very special design and understanding to overcome the ESD. But the reason behind the ESD is because of inside the MOSFET, we have this PN structure that can cause the issue of the ESD. But we won't talk in here, just for your information. Okay, so the next is also, we try to combine the two different of the semiconductor together. And that's usually we call the heterojunction. So, for example, the LED or the laser diode, and the third one is the HBT, which is the heterojunction bipolar transistor. And also, the last one is what we call the HAND, which is a high electron mobility transistor. And in here, we won't talk too much about all these, just want to show you that how actually the semiconductor A and semiconductor B, if we try to put this material together, what would be the device look like? For example, in the gallium nitride hand, which is a combination of the two different material, and therefore the typical schematic for the GaN hand, which is gallium nitride, and then we put another aluminum gallium nitride on top of the gallium nitride. So that's already the two different semiconductors together we put on top of with each other. So that's in the end become the gallium nitride hand. So the gallium nitride hand is mainly used for RF and power application, and this is because of that with putting the aluminum gallium nitride on top of gallium nitride, we will have the formation of the electrons here, and this formation electron is we generally call as a two-dimensional electron gas. That's what we call the 2DEG. So that's the key property to enable the GaN very suitable for the power and RF application. And that's why also this is one of the examples that once understand what happened in the interface, in the junction, will help us to understand the gallium nitride hand operation. Okay. So we will stop here for today's class, and we will come back later for the continue for the materials and solid introductions. So if you have any questions, just feel free to let me know, and we will see each other next week.